All right, so part two. All right, so let's look at 1.5. Let's select the whole thing. Hit the space bar and hide it. So with this file, we're going to be talking about parametric space versus Euclidean space. One additional thing, a lot of these components are disabled. So in order to enable them, we just need to select them, hit the space bar, and click on enable. So parametric space, as you guys saw earlier, is different from Euclidean space. Parameters in three-dimensional space or in surfaces have a u and a v value, right? Whereas in lines or lines, curves, etc., how many values do you guys think we have to describe a line parametrically? Just one, right? Because we can evaluate a line on a parameter. So what would be the zero parameter of a line? The starting point, and the end point would be 0.1. Sorry, 1. And the middle point would be 0.5. Grasshooper has this really nice component that's built in. It's called the MD slider. So it's basically a slider that works in parametric space from 0 to 1. So I find this component particularly useful in explaining parametric space. So if this were to be a line, parameter 0 would be the starting point, whereas parameter 1 would be the end point. 0.5 would represent the middle or the midpoint, and so on and so forth. If we're talking about surfaces, we have a u and a v value, where 0, 0 is the starting point of the starting corner of the surface, and 1, 1 is the end point. So it's a really nice abstraction, this component.
But it only does it like on this, I guess, surface or the plane here.
So yeah. So
it doesn't have that.
yeah, because here we're just looking at this plot, which goes from 0 to 1.
Okay. But if it was on the surface, that it.
If it was on the surface, it would exactly
on the face of the surface.
Yeah, the point or the z value would be according to the shape of the surface. Yeah.
So this is a slider, it's a different type of slider, right?
It's a two-dimensional slider, right? Mm-hmm. So there's this other very important concept in a parametric space versus Euclidean space, which is the concept of remapping. You guys were able to enable this this part of the definition, right? All you have to do is select it, spacebar, and enable. So the concept of remapping is super important. So in parametric space, everything goes from 0 to 1, or vice versa. We can remap whatever scale we are in into a different scale. So it's kind of like changing the domain.
Meaning that you want to be bigger?
I want it to be bigger or smaller,
Okay.
and that's really important. So let's say within the domain 0 to 1, 0.5 is the middle, right? But within the domain 0 to 10, what would be the middle? 5. So if we want to remap between different domains, there is a very useful tool called remap. So what I'm doing here is, let's start from scratch. Let's copy and paste this empty slider. So this goes from 0 to 1. So that's a little bit constraining. What I'm gonna do is decompose this vector. If you guys look at this is actually a vector. In this case, the vector is 1, 1, 0, 0. So this is a vector, so I can decompose it. If I decompose a vector, what am I gonna get? I'm gonna get an x, y, and z value. So let's type deconstruct. Okay. So this component basically deconstructs into x, y, and z, whatever it's here. Okay?
Is it attached to any environment?
Yeah, it's attached to this slider, which actually, because the slider is not a point on itself. It's a vector. It's two values in this case. It's a 0 and it's a 1, or a 1 and 0. But conceptually, it can also be a vector. It's just two values, right? So what if I want to remap this value from a domain from 0 to 10 instead? I'm gonna double click and type remap numbers. And this takes a value to remap, a source domain, and a target domain. So what would be the source domain of this particular vector?
0, 0.
The source domain would be 0 to 1. 0 is the smallest, and 1 is the largest. Okay? So I'm going to type construct domain. And we have a number of different domains. We have a two-dimensional domain. A two-dimensional domain is useful for like surfaces, things like that. And a one-dimensional domain, which is what we want to use in this case. So construct domain 1D, this one. Takes an A value and a B value. Why do you guys think this is not called starting and end values? Because a domain can have the values flipped. The domain, if a domain can go from, I don't know, -1 to, I don't know, 5, or from 5 to -1. So the order is kind of like indifferent. So in this case, my starting domain is going to be 0, and my B domain is going to be 1. What will be my target domain?
Whatever you want.
Whatever I want it to be, exactly. So I'm going to reuse this one. I'm going to say this one goes to 11.0. All right. So this x that used to be 1 is going to be now what? It's going to be 11. Okay. So I'm going to do the same, but with the y value. Okay, and I'm going to construct a new point with this. See? So you guys notice what's going on here? Look at these 2 points. They have the same direction and the same origin, but their length is different. And that's because they are remapped. The first point, this one, the one on green, let me change the color so it's a bit more visible. So better? Yeah. So this is our starting point, and once we remap it, it turns into the red one. See? Same direction, same origin, just different length. Now we're gonna deal with something else. We are gonna create a line between these 2 points. That's my line. And now I'm gonna evaluate the line. So double click and type evaluate curve. Okay, so what is t? T is the value that we want to evaluate the curve on. There's one important concept here, which is the concept of remapping the curve, reparameterizing the curve. In general, curves are going to have a domain that may be unknown, and the domain is dependent on the length of the curve. But let's think about making the same operation, or repeating the same operation in a number or a list of curves. If all the curves have different lengths, it's going to be very difficult for me to define the midpoint on each one of them, right? So how do you guys think we would be able to use the same parameter on all the curves? What can we do with the domain of these curves? In a similar manner that we increase the value, we can shrink the value between 0 and 1. So if we take all the domains, all the possible domains of the curves and shrink it between 0 and 1, no matter what the original domain was, if we use 0.5, we're going to get the middle, right? So that's what reparameterize does. it takes whatever domain the curve is in and shrinks it down between 0 and 1. So if you right click on C and click on reparameterize, this automatically takes the domain of this curve from wherever it was to 0 and 1. So I can say 0.4 or whatever. And this point, it's a point in line equivalent to this t parameter. Good? Does that make sense? You want me to zoom out?
No.
Questions?
Okay.
Good? Okay, cool. So let's look at a 3D parametric space. If you guys grab all of this and enable it.
Carlos, can you check and see if it's recording or not? Does it just pop up when I'm after
I think it is because there is a green.
Yeah,
Okay,
it's recording.
okay.
I can see my voice here, I think. So here we have this giant surface that's kind of random. And it might have any domain. And I am evaluating the surface on U and V. So this definition kind of like illustrates the concept of a three-dimensional parametric space. The whole domain of the surface is reparameterized between 0 and 1, and we can evaluate it within a number of points. What do you guys think would happen if instead of passing just one UV coordinate, if I pass in multiple? How many points would I be getting in? Multiple, right? So same as the other components, if you pass in a list, you get back a list. So is this clear, parametric space? Because this is really, really important. Okay, cool. All right, now let's look at this other definition down here. I have the same surface, and similar to the image that I showed earlier, every surface is composed by what we call isocurves. So we have curves on U and V direction. So all the NURBS curves are composed by quads or quadrants. And all these isocurves are in theory infinite, right? We can subdivide any curve in a number of isocurves. And we can do other useful things with all these curves. So in this case, I have a surface. And if I want to get isocurves, all I need to do is double click and type isocurve. And this component is going to want a surface and a series of U, V coordinates. The U and V coordinates are going to be the number of divisions that we're going to have. And again, as similar to the curves, we want to reparameterize the surface So the domain is always between 0 and 1 instead of 0 to whatever, right? So I'm gonna plug this in, and a very easy way to create a number of UMV domains is by using ranges. Different than a series, a range takes a domain. So let's say my domain for this particular operation is going to be between 0 and 1. And then subdivides this domain in a number of portions or numbers. So let's double click and type domain. Range. So the default is 0 to 1, which is what we want. And the number of divisions. Let's say, I don't know, 20. We can copy and paste this, and let's say 11 for the other one. Now we have two ranges with equal spacings. So when we have 20 divisions, the spacing is 0.05, right? So now all I have to do is put this two domains together into UV points. One quick way of doing it is constructing a point oriented on a plane. So you guys go to the vector tab. There are a number of different ways to construct points. What we're going to be using is point oriented. See, it creates a point from a plane, UMV coordinates. So this basically takes UMV coordinates and returns a number of points. So what happened here?
That was the question.
Does this make sense?
Yeah.
Yeah?
Basically, you just divided it more.
Yeah. And the number of range divisions on V equals the number of isocurves, right?
How can you integrate MD slider here? With that UMS slider.
An MD slider.
MD slider.
An MD slider. So let's say I want to evaluate based on this slider.
Yeah.
I can do it,
Okay.
but I would only get
Just
2. So the value of UMV would be the X or Y axes in this slider, and the point of intersection is of course the word X and Y intersect, right? In this case, it's, let's say, 0.5 and 0.5. So U equals 0.5 and V equals 0.5, and they intersect at 0.5, 0.5. What I did with this was basically replicate the same operation a number of times. So that's why I have a number of curves. So they go from 0.5 to 0.03, let's say 10 and 10. Right? 0, 0, 0.1, 0.1, 0.2, 0.2, 0.3, 0.3. Good? Okay.
So they're always divided into equal lengths.
Not necessarily, which is what we're gonna look at next.
Okay.
In general, with a Grasshopper and this type of sort of like linear coding or linear way of dividing space, it's very easy to replicate the same operation over and over. If we want to introduce non-linear operations, it's a little bit more complicated, but we can do it. And one easy way to do it is with graphs, which is what we're going to be looking at right now. So look at this definition. We have a random surface. Then that then gets subdivided into smaller quads. But the division distance or the length of division is not linear, right? And it's been modified by these handles or this graph. And it's all happening on the fly. So it's cool, but do you guys know why this is happening conceptually? No? Okay. So what's going on here is that we are first dividing this surface into equal number of parts. Let's say 10 and 10, so this is more clear. 10 and 10. Okay, so when we divide the surface into 10 pieces in U and 10 pieces in V, we get the same type of domain divisions as we did previously, right? 0, 0, 0.1, 0.1, etc. Conceptually, what we're doing here is taking these domains and we are modifying the extension or the kind of like the step size between numbers based on this graph. So in general, the data is linear in Grasshopper. So it goes 0, 0.1, 0.2, 0.3, 0.4, 0.5, etc. So it's all a single line, right? But when this data that comes in as a single straight line gets parsed or gets kind of like modified according to this curvature, the spacing of the points is not linear anymore. So conceptually, what's happening is that every point is being mapped to the graph. So it used to be all straight. So whatever was 0, 0 is still 0, 0, right? But what was 0.1, 0.1 is now down here. 0.2 is now down here, etc. So we're kind of like remapping the spacing. and it's no longer linear. And this line has an infinite number of divisions, right? Because these are surfaces, and the world and the space is continuous. So we can subdivide in X number of shapes. So that's what's going on here. And this is kind of like one of the hardest things to understand when you're dealing with parametric space. How to remap and how to deal with parametric space compared to Euclidean space. Yeah? Questions? All good? Maybe? Uh-huh.
When deciding, between these different kinds of graphs,
Mhm.
Can you explain why you would choose a conic over say, parabola or something like that?
Yeah. So it just depends on the type of control that you want to have, and whatever shape the graph has is the shape your data is going to have. So if you have a parabola, the only two parameters that you can change on the parabola is oh, I think I killed your grasshopper. Let me, I'm gonna have to restart it. So yeah, it just depends on how much control you have over the graph. That used to happen way more often in earlier versions. And in general, the shape of the graph resembles the shape of the data. And it sort of like depends on how much control you want to have over it. So of course, a conic, instead of having two handles or you being able to modify it in both ends, you can only modify it at the beginning of the graph. So with a conic, instead of having control over the edges, you only have control from the middle to the sides. The nice thing about visual programming is that it all happens on the fly, and as you see it, you can sort of like make sense out of it. Good. Anyone else? Okay, cool. We can skip. Well, let's look at vectors, because vectors are important. So you guys can open 1.6. So vectors have a number of properties and have a number of operations. For example, if we look at this vector that I'm creating here with the MD slider, a vector has a length. It also has an angle. The angle is it's always in radians, and it's always according to the xy plane. We can always get a unit vector. What's a unit vector? It's a vector with a length of 1. So the unit vector of this vector would be exactly the same vector in this case. So it's a vector with whatever direction. The only difference is that the length is always going to equal 1. We can also modify the amplitude of a vector, make it shorter, longer, etc. There are like a number of different properties that you can play with. You can do this on your own. Yeah, I think I'm gonna skip this vector geometry because it's too abstract. Yeah, and I'm gonna go to how to construct a curve from numbers. So if you guys open 1.7, we're gonna look at how to construct a mathematical curve. So have you guys seen like sine curves or all this type of geometry? How do you guys think we can construct a sine curve? What do you know? Yeah, one easy way to do it is whatever is changing on the sine curve is the amplitude, right? So we can first, let's do it from scratch. We can first define a range. Our range is going to go from 0 to 1. Let's say we want 20 divisions. And now we can construct a point with this, or number of points. Okay, so all of them have equal spacing, and all of them lie on the x axis. So I can modify the amplitude on y by multiplying each one of these values by a sine or a cosine or whatever, right? So let's double click and type sine. And now this gives me part of a cosine curve. What am I missing here? What's the amplitude of a cosine curve? 2 pi. So the domain, instead of being from 0 to 1, is going to go from 0 to 2 pi, right? So that is one cycle of sine curve from 0 to 2 pi. Right? Does it make sense what I'm doing? Yeah? Okay, cool. And then I can simply create a polyline with all these points. Cool, that was easy. I'm gonna switch the rest of this. You guys can look at it on your own. But it's like the basic concept. We get a constant, in this case a mathematical constant, and we modify the values x, y, or z based on this mathematical constant. The important part of this is that all of these math constants are kind of like periodic, so they repeat each other, and that's why we can get this type of periodic curves type of data. Let's look at 1.8. 1.8 is not very relevant to us today. Okay, lists. Lists are very important. We have been working with lists, but so far we haven't really manipulated lists beyond shifting one of the elements of the list. So let's say we draw a curve in Rhino. One important thing that we haven't talked about is how to bring geometry from Rhino into Grasshopper. So first thing that I'm going to do is draw a curve in Rhino. So instead of typing on the Grasshopper screen, I'm going to click on Rhino and I'm going to type curve. I'm just going to draw a random curve. Gonna hit enter again. I'm going to draw another random curve down here. These containers can also link geometry from Rhino into Grasshopper. So if I right click on the curve container and click on set one curve, this lets me select whatever curve I decide. So just click on it, right click, and click on set one curve. Whenever I set the curves, the geometry in Rhino gets automatically added to Grasshopper. If I erase one of these curves, Grasshopper also loses its data. Okay, so the first thing I'm going to do is divide this curve, or these two curves, into a number of points. So you guys are familiar with this divide curve components. And now what I'm going to do is, instead of creating lines between all the points as we had before, I just want to create a line between specific elements. So let's say I only want to create a line between 0.0 and 0.5. I need to be able to select this specific set of points. So I'm going to double click and type list item. So list item is a component that lets me retrieve whatever element from a list. So we need a list and we need an index, basically. So let's say I want to grab the first element of the list. What will be my index? First element of the list. 0, right? Because we start counting from 0. Okay, there we go. First element 0. Second element 1. So on and so forth. Okay, so if I copy and paste this down here, now I can also select points from the other curve too. So now instead of creating lines between all the points, I'm just creating a line between the points that I selected, right? Does that make sense what's going on? Yes, no?
I think for you're making it like more intentional rather than random.
Yeah, well, it's not random. It's just matching list with list.
Yeah.
So I'm just selecting, from this list, I'm selecting one element.
Yeah.
So the fifth element in this case is 4. So here it is, right? So I'm kind of like selecting or picking just one specific element. So that's the first thing. List item is what we just saw. The lists have a number of different other properties. How would I be able to grab the last element of a list if I don't know the list length, or if I don't know how many elements are in the list? Any ideas? Let's say I have 5 lists. The first list has 2 elements. The second list has 20. The third one has 40. Fourth one has 50 or whatever. How can I grab the last element of all the lists without having to type individually the length? I can ask Grasshopper how long every list is. And then I can use that number as the input, right? So let's do something like that. In this case, my first list has 22 elements and the second list has 12. If I want to grab the first element, that's easy because it's always going to be 0, right? But in the second case, if I want to grab the last element, it's a little bit more complicated. So first list has 23 elements, the other one has 13 elements. So let's try to grab the last element of the list with this with those components. List item. So we have list 1 and list 2. So what's the index, or what is the index of the last element in list 1? It's 22, right? What's the last element in list 2? It's going to be 12. But what am I getting here? Length is 23 and length is 13. What do you guys think if I try to use these numbers as the index or the indices of the list? It's not going to do anything. Why? Because we start counting from 0, not from 1. So we need to subtract one number. See, so it gives me the first number, because it kind of like wraps around, but that's not what I want. So if instead what I do is subtract 1 from this value, I use that as the index. I'm always going to get the last element of the list. No matter if I change the number of divisions, I'm always going to get the last element. And that's why Grasshopper is parametric. Does that make sense? because we keep the same parameters constant, and no matter whatever input we get it, it's always going to apply the same set of rules. And that is super useful. There are a number of other properties. We can reverse the order of the list, which means we're just flipping what goes first. Shift, we already talked about shift. It basically just modifies n numbers the list order. We can split the list into two. We can get subsets of lists. So from a list, just give me from index 2 to index 5 or whatever. We specify all these lists. So all of these are kind of like ways to manipulate lists. And this is super important. Okay, this one is the first one that is kind of fun, or it gives you something useful. So the first thing, we're going to build all of this from scratch. How do you guys think we could be able to get a point field? So a big field of points. How would you guys go about it? One idea?
Create points and move it.
Yeah, we can create points and move it a number of times. So let's try your idea. Construct point. Okay. Now what do I do with this point? I'm gonna move it, right? So let's first move it in X. But that gives me only 1 point, right? What if I want to move it more than once? I can pass in a list of values, right? So how do I make a list? Let's try with series. So the series component gives me, by default, a list of numbers from 0 to 9. So if I plug this in, I got 10 points, right? Now what do I do?
Move it into Y.
Yeah, I need to move it into Y. But what do I move? Do I move this original point, or do I move this ones? Let's try moving the original one. Just gonna copy and paste this down here. Instead of using an X, I'm gonna use a Y. What happened? It moved the original point in Y. Does all of this make sense? What if I want a field instead of 2 columns? What would I have to do differently?
Range.
No, all I have to do is move these points. But not like that. You guys realize what just happened? What did I just do? All right, this is another very, very important concept. And it has to do with the data structure. Okay, so let's look at our list of points in X. All the points have a Y value of 0 and a Z value of 0. The only thing they change is the X value, right? And what do I have here? I have one single vector, or one vector for each point, right? So what's happening right now? Every point is being moved by this vector. So point 0 gets moved to 0, 0. Point 1, this one, gets moved to 0, 1, and so on and so forth. That's why I have a diagonal. But what do I actually want to do? What I actually want to do is move each point 10 times. So how do I do that?
I guess you press the graph.
Yeah, I press graphed. So what graphed actually does, I'll do it with another component. Graphed. It takes this list and makes 10 lists, right? So it's kind of like a list within a list. So earlier it was one single matrix of points. Point 0, point 1, da da da, point n. And when I graphed it, when I multiply this by a vector, it's all linear. It's all mapped to the same vector, right? It's like I have one single list of vectors. So it all matches 1 and 1. But when I graphed it, I create an individual list per point. Which means that now every list needs to match to all the 10 points, right? So I'm kind of like matching, instead of 1 on 1, 1 on 10 now. That's how Grasshopper works. It's about list matching and data matching. So now when I move these points 10 times each, I get this big field of points. Make sense?
Yeah.
Let's make this field even bigger. Let's get like 50 points. Maybe 50 is too much. Right, something like that. Now let's make something cool. What if I want to draw a circle on every point? What would I have to do? Yeah. The cool thing about this is that the output is going to be a series of points. It's a big list of points. So if I type circle, and I get a circle component, and I attach that to the output of move, it's going to create a circle on every point, right? And that is cool, because I didn't have to draw each circle by hand. Now let's make something even more interesting. Right now I can change the radius of the circle with a slider, for example. But what's going to happen if I change the slider value? It's going to make the circles the same size, right? Because it's the same parameter applied to all the list. What do you guys think I would have to do if I want to modify individually the size of every circle?
Random.
Yeah, I can make it random. That's a good way of doing it. But what if I want it to be meaningful? You guys start thinking more specific to your own projects.
Do you change your list?
Yeah, you have to manipulate your list according to something. But let's say you want in your projects, some of you are dealing with sun or wind or whatever. What if you want to manipulate how open or how close each one of your modules is according to wind or sun? You can start adding rules or model a sun system and modify the thresholds, and that kind of like maps to the radius of the circles. But today we're going to do something different. We're going to use something that we call attractors. So an attractor is basically a point that we use to modify a value. So I'm gonna go back to Rhino and type point. Gonna get a point somewhere in here. Let's click here. And then within Grasshopper, I'm gonna type point, because I want to be able to reference the point that I just created in Rhino into Grasshopper. So this point container is gonna be my attractor. So once I get the point, and I can click on it and right click on it, set one point. Right? Let me change the color of this.
You think I can turn off the gaze mode? So distracting.
Sorry?
You can turn off the gaze mode.
Oh, I don't know how to do it.
It's in the status bar. If you close your Grasshopper, it's there. Just turn off
Gumball?
the gumball, yeah.
Okay, cool. Okay, so this point is my attractor. So what I'm gonna do is calculate the distance from every point or every circle center to this point, and then I can use that distance as a radius value, right? So what's gonna happen with whatever is very close to the point? It's gonna be smaller. Whatever is far away, it's gonna be larger. So it's like a very simple way of starting to think parametrically about geometry. The cool thing is that this distance operation is going to be replicated among all the points. All right, so let's double click and type distance. So we're going to get the distance between point, the attractor point, and all the points. And this magically is going to give me a list of distances, right? So from 25 to, I don't know, 1, 2, whatever the minimum distance is. So what's going to happen when I plug this into here? Now, every point is going to have a different, or every circle is going to have a different radius. The radius is very big right now. What's one easy way to make this radius smaller? We can divide it by a large number, right? So double click and type divide or division. Let's divide it by, I don't know, let's say 101. Now the circles are tiny. Right? This is cool. And if I move the point, the whole field changes, right? So you guys can start thinking about your systems following some vectors or changing according to these values easily, right?
So you got the point. The radius that is assigned to each circle depends on the distance from that attractor. So if it's further, it's bigger. Wherever it's closer, it's smaller.
Mm-hmm. Yeah?
Yeah.
All right. One bonus question. Right now, the maximum and minimum radius are kind of like arbitrary, right? What if we want to constrain it within a domain? What can we do? We did it earlier.
Yeah. Do you remember when you don't have any idea about the domain, where it starts and where it ends?
You make it.
We can remap it.
Remap it.
So we remap it from a source domain to the domain we want. So let's try that before we go. Let's double click and type remap. So all the numbers are going to be whatever the distance is before we divide it. What's going to be our source domain? The largest and the smallest value within the list, right? But there's one problem. We have no idea what the maximum and the minimum are, do we? No. Because these distances are kind of like arbitrary and they change all the time. So whenever I move my attractor, the minimum distance, this is the minimum, changes. So I wanna build a definition or an algorithm that's very robust. So every time I change it, nothing breaks. I still get the same result, right? So one way of doing it is getting the bounds of a domain. So if you double click and type bounds, bounds give you the minimum and the maximum value. But there's one problem. Right now, if you look at this, the structure of the data, it's multiple lists, right? It's like a number of lists within a list. And why is that? If we go back here, exactly.
Yeah.
We grafted it. So what do we have to do now? We have to compress it into a single list again. So that is called flatten. So we take this really nicely structured list and we flatten it into a single list. So we can right click on it, or we can get a flatten component. So let's do the flatten component, flatten tree. So this is gonna take a list, and it's gonna flatten it into a single list. Do you guys see the difference even with the cable? Lists of lists have like this dotted, kind of like discontinuous cable. Single lists have like this two lines, right? And single elements are just a single line. So graphically, Grasshopper is helping you figure out what's going on inside each one of the components. So now that I flattened this numbers, instead of getting 10 domains or 20 domains or whatever, I only have one domain, which is always going to give me the smallest and the largest. And what's cool is if I modify the position of this point, the domain changes on the fly. And that's really cool. All right, so now I have my source domain. And my target domain is going to be my minimum and my maximum values. So let's say I want, well, first let's double click and type construct domain. So this is going to take a small value and a large value. Let's say my smaller value, I want it to be, I don't know, 0.05. And the largest value, I want it to be 1.15. So now I'm going to make sure that the largest number within this division is 1.15, and the smallest one is 0.05, right? So if you look at this list, nothing is larger than 1.15 or smaller than 0.05. Since the separation between each number is, I believe, 0.5. If we wanted to never touch each other, we can use 0.5 as the maximum number, right? Make sense? Yeah? You want me to zoom out? Do you guys know what's going on?
Yeah.
Yeah? Okay, cool. So I think we're gonna leave it here for today. You guys got a lot of information. You guys should go back to a lot of the definitions that we looked at today and kind of like revisit it and sort of like make sense of what's going on. And for next, on Monday, you guys should collect a number of questions, a number of things that you want to do. And I have material prepared, and we can do like a mixture of question and answer, and also go through the rest of the definitions.
So, but
Sounds
it's
good.
important to make yourself familiar with all these things because